Hello, my name is Pratik Chandrakant Male. My roll number is 3031. Today, we are here to present the ISO of theory of computation, and our topic is PDA, that is push down automata. So here we present. So firstly, I am presenting the what is PDA. So PDA is the push down automata used in theory of computation to recognize the context-free language. So here, as we see in this PDF, the push-down automated computation model that uses a stack for temporal memory. It is like a finite automata, but it have the dynamic memory. In finite automata, there are limited storage. We store the limited finite number of states, but PDA stores the infinite number of states because of using stack data structure. It helps to recognize the context-free language which are not possible with finite automata. So here there is the different symbols used in to represent the PDA. So first symbol is a Q, means Q represents the set of states. Uh, After that, sigma means input alphabet that are we like A, B, we pass into the stacks. That alphabet is represented by the sigma. After that, gamma is the stack alphabet, X. If we put the A to the stack, then the top of the stack is X. This is represented by the gamma. Here is the delta is the uh, transition function. After that, q naught is the start state, it is the initial state that the machine is started. Z naught is the initial stack symbol, and if is the set of final state. Final state means acceptance state, states where the our grammar or language is accepted. So here we see the example of the PDA. So language L is equal to a raised to n, b raised to n, and n is greater than 0. Means number of a's and number of b's are equal. So we see the deterministic PDA. The DPDA is a PDA where every combination there is only one possible transition. No ambiguity in moves, means there are no double meaning moves is present in the DPDA. No epsilon transition allowed, means not null transitions allowed in input transition is possible, and used to recognize deterministic context-free language. Here is the example: a raised to n, b raised to n, n is greater than 0, L is equal to a raised to n, b raised to n. For each a, push into stack and each b, pop from stack. Here we see the steps. In first step 1, input is a, b, b. So stack top of the stack is z naught. We push the a, then remaining input is a, b, b. So top of the stack is a. After that, we push the next alphabet a. So this remaining stack is the the remaining language is the bb, and in stack there are two a present that we pushed a z naught. After that, we push b. After input b, there we perform the push operation. Then first a will be destroyed. After that, pushing the next b, there is null symbol, and our string is accepted. So we see the configuration of PDA. So what is PDA? What is the configuration of PDA? The configuration of PDA records the current state, remaining input, and the stack contents present in the every language. So it shows the three notations. Q represents the current state. Mean the alphabet in present in that state. W is the remaining input, and sigma is the stack content. So here is the example: the PD in state Q1 with input A, B, B, and the stack XZ configuration of Q1 A, B, B, XZ. Explanation: here Q1 on reading A, when the input top of the stack is X, the X, then push another X. Here as we see here, we configure the PDA.
From now onwards, I am presenting from here. So my name is Neha Vijaykumar Sakri and my roll number is 3032. Let's see the acceptance by empty stack. The PDA accepts a string if the stack becomes empty after reading the full input. So the notation for this is a Q naught on reading string, that is W. We are noted here. Top of the stack is Z naught tends to state, that is a Q, and null on reading null. So example of this notation PDA is language L is equal to a raised to n, b raised to n, and where n is greater than or equal to 0. So I have created this table where there are three steps, and input is a small string taken as a AB, and this is the stack column, this is the action column. Let's see one by one. So first step is that there is our input is AB, so the stack at that point is Z0, and action is push A. By pushing A, the stack fills A Z0. So after that, the second step, that is a there is a input B, and the action at that event is pop A. Means by reading the input B, we pop the element A, and the stack remains now Z0. So here then the third step is that by input reading is there is a no input right now, that means the null input, and the top of the stack is Z naught, and the action is that stack is empty, and this string is accepted by the PDA machine. Explanation is that here PDA accepts a string without requiring a final state, just by emptying emptying the stack. So this is the example where it not require any stack elements. So means it by emptying the stack, it is accepted. Now let's see about the acceptance by final state. A PDA can also accept by entering a final state regardless of the stack content. Means whatever the content in the stack, it is accepted by the final state. The notation is Q naught on reading string input string, and top of the stack is Z naught tends to final state epsilon, that is a null input, and content of the stack. Example of this, same language L is equal to a raised to n, b raised to n, and where n is greater than or equal to 0. But PDA accepts when it reaches final state QF after consuming all inputs. Explanation is about this example is acceptance by final state is useful in cases where stack content may remain after valid input recognition. Means uh, a, a string is recognized correctly and then it is accepted. Now let's see about the converting context-free grammar to top-down PDA. So the given grammar is S tends to A S B A, and A tends to B A S and epsilon. This CFG can be simulated using a top-down PDA. The idea is that start with a start symbol S on the stack, then replace variables using grammar production top-down approach like that, and then match input symbols with the stack terminals. So let's see this one by one. Now PDA components. PDA machine is equal to Q, sigma, gamma, delta, Q naught, Z naught, and F. Let's see about these representations. So Q represents the set of states, sigma represents the input alphabets set, gamma represents the stack alphabet set, delta represents the transition function, Q naught is the initial state, Z naught is the uh, stack element, first initial stack element, and F sets represents the final state. So the components and descriptions are here. So first component is that Q, description is in a set Q. Then sigma in set A and B. Gamma in set S, capital A, small b, and Z naught. And Q naught, that is the initial state, is that Q, and Z naught is capital S, and final state is Q again. Let's see the transition rules for this example. So here are some transition rules and their meanings. Let's see one by one. So first one is that when PDA is in a stack Q and there is a no input symbol, that is a epsilon or null, and the top of the stack is capital S, then we replace capital S by ASB. Then likewise we replace capital S for as capital A. Then the third rule is that when PDA is in a state Q and there is a no input symbol but the top of the stack is capital A, so we replace capital A by B, capital A and small a. Then the PDA, when it is in state Q and there is no input symbol and the top of the stack is capital A, so we replace the capital A to capital S. Likewise, there are one more rule about the same thing, that we replace capital A to null. Then the next rule is that when PDA is in a state Q and the first input is A, so and the top of the stack is A, so we get the match A. Then the same like with B, so PDA which is in a state Q, the input symbol is B and the top of the stack is B, we get the match for B. By using that transition rules, we solve the grammar conversion example, that is a ABBA string. Let's see one by one how it is executed. So check if a string ABBA is accepted or not. So first step is that start step, and the stack have S and input is ABBA. Second is that replace S with ASB and the stack has ASB and input is that ABBA. Here we use the rule, and then the third step is that we get a match A when stack is SB and the input symbol is BBA. And fourth step, replace S with the A, that is AB and input is BBA. Then replace A with a null, then we have elements in a stack only B, then input is that BBA. Then the last step is that we get a match with B, B and A, then the stack is empty and input symbol is also empty. The stack is empty, that means string ABBA is accepted. Explanation is that top-down PDA mimics a grammar derivation. Every production is push or a pop operations. Likewise, we solve this string and recognize this string is accepted or not by the grammar conversion with using the transition rules before I have stated.
So let's take an example for PDA, which is a raised to n and b raised to n, and where n is greater than or equal to 1. So let's start it. So this is the Java JFlap extension made by Java, and here we can do machines, and by using these applications we can we can check the input string is accepted or not. So let's make the machine for a raised to n and b raised to n. So I'm taking here states q0, q1 and q3 and making the q0 state as initial state and q2 state as a final state. Then let's add the transitions. So for this, for q0 I am adding the transition here, input A, on reading stack is that Z, the output is that A Z. Then for the same Q naught state, the input A on reading stack A, output is AA. Then when input is B and the on reading stack is that A, null operation, it goes to the state 1 from Q naught state. And on Q naught state, here input is B, on reading top of the stack that was A, there is no operation. Then from Q1 to Q2 state, there is a null input, on top of the stack is Z, then result is Z. So this is the machine, PDA machine for A raised to n and B raised to n, where n is greater than or equal to 1. So let's check it out, it is running or not. By clicking input, step by step, I am giving input AA, BB, click on OK and OK. It is accepted. So let's see the step-by-step conversions from first input to the last input. As you can see here, there is a box opens where the upward is that our input, and this is our stack which have the initial element Z. So let's start it. First one is step. As you can see, the first A is readed and here stack is filled with AZ, where here A is pushed here. Then on reading A here, see in the diagram as well, Q naught state, on reading A is Z, on reading A, the top of the stack is Z, the stack is filled with AZ. Then on reading A, the top of the stack is A, the stack is filled with AA. Likewise here you can say the stack, our stack AAZ. Then again clicking on a button step, by reading the input B, the top of the stack is A, the state changes where it is goes from Q0 to Q1 and the pop operation of A element is done. So the stack remains now AZ. Then again I am clicking on a step 1 step. So by reading input B, the A is popped and now there is only Z element in our stack. By clicking again, it is accepted, means by there is a no input, that means here you can see there is a no input here in the input string. So by reading the epsilon, that is a null value on top of the stack Z, it goes there is a no operation here and it is accepted. And as you can see on the application, there is a green color appears or a bluish color appears. So this is the accepted, this string is accepted. So now let's test about the taking another input. I am taking A, B, B and A. So let's click on OK and OK. So as you can see here, now the input string is A, B, B and A, and the initial stack element is Z. So let's start it step by clicking step. As you can see here, Q naught state have a Z and AZ and A and AA. So by reading A element, it push A into the stack. Then again by reading A element, it pushes A in the stack. Then by reading B element, it pops one A. Again it reading by element B, it it pops the element A, and now there is only input is A and the stack element is only have a element Z. So by clicking step, then it can't read A, and by clicking it again, it appears the it is rejected string and it appears on our J flag, that is it is not a accepted string, that's why it comes the red or pinkish color here. So it is a rejected string. So as you can see here, we can accept only A raised to n and B raised to n elements. Other than that, our machine, PDA machine, rejects the string. Thank you.
My name is Rajnandini Jadhav and I will explain the next part, that is the deterministic PDF for equal number of A's and B's. So these are the transitions given in the slide. I will explain it by constructing the PDF for this, that is equal number of A's and B's. So let's take the steps, that is Q0 and Q1. This is our initial state and this is our final state. Let's make the transitions on it. First it will create the loop when the input is A and the top of stack is a Z. Then it push the A on the stack. Then stack becomes A Z. And when input is A and the top of stack is also A, then it push the A. When input is a B and the top of stack is a Z, then it push the B on the top of stack. When input is a B, also B, and the top of stack is B, then it also push it. When input is A and the top of stack is E, then it pop the A. When input is a B and the top of stack is A, then it also pop the B. Then on the input null, it goes to next state. That is, input is a null, top of stack is a Z, and it remains the same. So these are the PDF for the equal number of A's and B's. So let's simulate it by taking the input of equal number of A's and B's. So these are our input and this is top of stack. Firstly, it is in initial state. After simulating, it goes on the final state. So after that, the next example is for unequal number of A's and B's. So these are the transitions. I will explain it by drawing the PDA. So first take the states Q0, Q1 and the Q2. This is our initial state. This is our final state. Let's make these transitions. First, it creates the loop on itself when input is A and the top of stack is A. It pushes the A on the stack, then stack becomes A's head. Then it also creates loop when the input is A and the top of stack is A. Then it pushes the A on the stack. On the input B, it goes on the next state. That is, input is A and the top of stack is input is B and top of stack is A. It pop the B when it will create the loop when input is B and the top of stack is A. It pops. When and the top of stack is A, it remains as it is. It performs no operations. Similarly, when the input is B and the top of stack is Z, it remains as it is. It performs no operation. So this is a deterministic PDA for the unequal number of A's and B's. So let's simulate it by taking the unequal number of A's and B's. So as shown in the slide, I will take this input. So this is our input. This is top of stack and it is now in the initial state. After simulating, it goes on the final state. So next is the summary. The concept we learn, it is a push-down automata, deterministic PDA, configuration, what is acceptance by empty stack, what is acceptance by final state, and convergence from the CFG, and examples of Grammar. And also now we see the construction of PDA for equal and unequal number of A's and B's. Let's conclude our topic. A PDA is basically an extension of finite automata. Hence, it adds an extra components called a stack, which provides an memory. There are two types, that is a deterministic PDA and non-deterministic. The deterministic PDA handles deterministic context-free languages, while the NPDA handles all context-free languages. And the top-down PDA is especially useful because it can directly simulate the derivations of grammar. Then PDA have some applications. It has many applications, especially the areas like parsing, compiler design, and the syntax changing, which are the essential part of the programming languages. So, overall, PDA plays a very important role in the understanding and designing the systems that processes the languages within nested or recursive structures. So, thank you.